Draw a dot plot, also known as a line plot. Basically what you're going to do is you're going to give yourself a nice little line. Let's look at the numbers we have. We just have a bunch of values. This is not a scatter plot. You're not making a graph or a line of best fit or anything like that. No bar graphs. This is just like, here's like if we were to say I'm selling ice cream and every day this is how many cones I sold that's vanilla flavored. That's what we're looking at. We're just trying to find out how many times we got 7 and how many times we got 4 and how many times we got 9 and stuff like that. So it looks like the smallest number is 4. The largest number is going to be 9. So 4, 5, 6, 7, 8, 9. And I did a great job spacing that out. Now, this is a dot plot, so we're going to use dots. Some classes use X's, but it doesn't really matter. And the way I do this to make sure that I don't make any mistakes because of my ADHD brain, we have one dot for 4, so let's put a dot there. Let's cross it out. We have 1, 5, and that's it, so put a dot there for 5. 1, 2, 3, 4, 5 sixes, so 1, 2, 3, 4, 5 sixes, 1, 2, 3, 4, 5, 6, 7 sevens, 1, 2, 3, 4, 5, 6, 7 sevens, an 8, and a 9. So again, that's your dot plot. And some teachers use X's, some teachers use boxes, I guess. I don't know. But this is a dot plot, also known as a line plot. And as we can see, the majority of our data hovers around this 6, 7 range. And we can kind of use this to easily figure out mode or estimate median, stuff like that. So hope this helps. Draw a stem and leaf plot. A stem and leaf plot is basically going to look something like this. I'm just going to make one up right now. If I give you 1, 2, 5, 6. And if I were to tell you down here that something like that means 17, then this is 12, and this is 15, and this is 16, and you would be 21, and you would be 28, and you would also be 28, stuff like that. So I'm going to do the same thing using this information that I see right here in front of me. And since I'm using double-digit numbers, I'm going to set it up kind of like the way I set up here when I made a fake example. So what we need to do is we need to make ourselves a key and say something to the effect that 3, 2 means 32. And what we really ought to do is come up with the smallest number, and that's not what we ought to do, that's what we have to do. We have to come up with the smallest number, and look at God, these are already in order. Oh, how nice. Okay. Well, that makes like life 1,000 times easier. So 3, 2 is going to be my smallest. Then I'm going to have a 4, 5, 6, all the way up to 7. So I get 4, 5, 6, 4, 5, 6. I get 1, 4, 5, 7, 8, 9. 1, 4, 5, 7, 8, 9. I get 0, 3, 4. We get 0, 3, 4, and last but not least, 70, 75, 79, 75, 9. And that's going to be your stem and leaf plot. Look how pretty that is. That's super pretty. Make a box and whisker plot based off of this data. Really quickly. This is the box and whisker plot. This is what it's going to look like, generally speaking. Okay, if I knew how to draw this, would be a lot better. This is the median. The guy right in the middle is the median. Now, this is called the lower extreme. That's the smallest number. This is called the upper extreme. That is the largest number. That is the first quartile or the lower quartile. That is the third quartile or the upper quartile. Now, what the lower quartile is the median of the lower half. Don't include the actual median. So let's do this first. Let's build, at the very least, our median, lower quartile, and upper quartile. Then we'll focus on what it means to be the median of the lower half and the median of the upper half, all right? God is good. Everything's already in order. So the middle number is 6. You are my median, okay? You are my median. So I'm going to put something here That's just going to be my thing. Now, my lowest number is 2. My largest is 13. So let's do 6, 7, 8, 9, 10, 11, 12, 13. And then we got 5, 4, 3, 2. All right. My smallest number, my lower extreme, is going to be 2. And my largest number, my upper extreme, is going to be 13. Now, the way I find my lower quartile, or my quartile 1, is I take the lower half of the data, exclude the median, and I find the median of that. So I have 1, 2, 3, 4, 5, 6, 7 numbers in the lower half. So the middle of those 7 numbers is 5. So 5 is going to be my lower quartile. So far my box and whisker plot is going to look a little something like that. Now the median of my upper half is going to be my upper half excluding the median, and it's going to be the middle number of that, which is going to be 7. So the middle number of that is going to be 7, so let's put a line there. Let's connect the dots. We have that 13 all the way out there, which is basically an outlier. And we built ourselves a box and whisker plot, okay? Lower extreme, lower quartile, also known as Q1, median, upper quartile, also known as Q3, and our upper extreme lives right there. Box and whisker. Find the mean, median, and mode of these numbers. Now, before I do anything, let's go in order and do the mean first. To find the mean, all you have to do is add up all the numbers and then divide by how many numbers you have. I have 1, 2, 3, 4, 5, 6, 7, 8 times 2, so I have 16 numbers. So I'm going to go off to the side, find out what all of these numbers are added together, and then divide it by 16. When I did that, I got 105, and then 105 divided by 16 is going to be 6.5625. Now that's my mean. In order to find the median, what I really need to do is list these numbers in order. So let me quick do that. The smallest is 4. All right, so let me just write them out here. 4, 5, I have 1, 2, 3, 4, 5 sixes, 1, 2, 3, 4, 5 sixes, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7 sevens, 1, 2, 3, 4, 5, 6, 7 sevens, an 8, and a 9, and that should do it. The median is the number directly in the middle, unless you have 2 numbers directly in the middle. Let's see what happens. So small, big, 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 2 numbers directly in the middle. Now, usually when that happens, the way you find the median, and I'm going to show the work anyway, even though it's going to seem like a waste of time. If you have 2 numbers in the middle, you add those 2 numbers up and then divide by 2. Now, adding 7 and dividing it by 2 is just going to give you 7, but I wanted to show the work anyway because why the heck not? It's my job. Now, the mode is the number used most often. Sometimes you have no mode if no numbers repeat. Sometimes you have several modes, but in this case we have one mode, and that one mode is 7 because that's the number used most often. So there you have it. Mean is the average, median is the number in the middle unless you have 2, in which case it's the average of the 2 in the middle, and mode is the number used most often. Find the mean, median, and mode of this information right here. Well, basically, if I were to take this information, this dot plot, and write out everything, I would write out a 1, 1, 2, 3, 4, 5, 6, 7, 8 twos. So 2, 2, 2, 2, 2, 2, 2, 2. 1, 2, 3 threes, 1, 2, 3, and 1, 2, 3 fours, 1, 2, 3 fours. My mean is done by adding up these numbers and dividing it by how many numbers I have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 numbers. So I'm going to go off to the side and find out what all of these guys are added together. So we got 38. And a faster way of doing it, I guess, is if you realize that that's just a 1 and there's 8 twos, or was there, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, there are 8 twos. So 1 plus 16 plus 9 plus 12 would probably be a faster way of doing it. But anyway, yeah, that's the way that you can do it. When you divide by 15, you end up getting 2.53 repeating. So we'll say 2.53 repeating. That's going to be my mean. My median is going to be the number in the middle, right? So I have small, big, small, big, small, big, small, big, small, big, small, big, small, big. And my number right in the middle is that 2. Now, if you were to have two numbers in the middle, add them up, divide by 2, but that didn't happen here. My mode is going to be the number that's used most often, and it's very obvious what my mode is here. My mode is going to be 2 because I have a bunch of dots living above 2. But I can also see here that I have 8 2's, so that's also going to be my mode. So there you have it, mean, median, and mode. Fun stuff. Find the interquartile range. The interquartile range of a data is found by taking your upper quartile minus your lower quartile. Now, the way you find this stuff out is the upper quartile is going to be the median of the upper half, right? So I'm going to have to figure that out in a minute. And the lower quartile is the median of the lower half. So what I'm going to do is I'm going to make sure that these numbers are in order they are, but I'm going to kind of rewrite them out. 62, 64, 69, nice. 70, 70, 71, 72, 73, 74, 75, 77. Let's find out what my median is. My median is the number directly in the middle. So small, big, small, big, small, big, small, big, small, big. So my median is 71. Now, the way you find the median of the lower half is you exclude this median right here. You're dead to me. And you find the median of the lower half. So the median of the lower half is small, big, small, big. The median of the lower half is 69. So you're my lower quartile. The median of the upper half is small, big, small, big. You are my upper quartile. So my upper quartile, the median of the upper half, is 74. I'm going to subtract out the lower quartile, the median of the lower half, which is 69, and therefore my interquartile range is going to be 5. Wasn't that fancy and fun and neat? It's great. Number 5 will always love you. Donovan McNabb said that. Like and subscribe. Find the mean absolute deviation. This is pretty gross. It actually makes me mad. Mean absolute deviation, MAD. Anyway, what you need to do first is you need to find the average, or the mean. Okay, so that's what we're going to do first. Find the mean of this whole set of data. Step 2 is we're going to find the distance of each data point from that mean that we just calculated. Okay, the distance means, like if my mean, say, was 70, which I don't know if it is. If my mean is 70, then the distance from 62 to 70 is a positive 8. Or the distance from 70 to 72 is a positive 2. So that's the distance. It's the positive length. Once I find all 1, 2, 3, 4, 5, 6, 7 of those distances, I find the mean of those distances. So before I can even do anything, I need to find the mean of everything. So that involves me adding 62 plus 64 plus 69 plus 70 plus 70 plus 71 plus 72. So the mean, step 1, is going to be me finding those guys added together divided by 7. Let me find out what those numbers are. Give me 1 second. So that ended up giving me 478. Now 478 divided by 7, according to Mr. Calculator, is a gross 68.3. Okay, so that's not going to be awesome at all. Not all, but I'll be all right. So what I need to do now is I need to find the distances from the mean for each of them. So I'm going to do 7 subtraction problems enclosed in absolute values. So that was step 1. Here is step 2, the distances. Okay, so the distances are going to be absolute value of 68.3 minus 62, the absolute value of 68.3 minus 64, the absolute value of 68.3 minus 69, the absolute value of 68.3 minus 70, the absolute value of 68.3 minus 70 again, the absolute value of 68.3 minus 71, and the absolute value of 68.3 minus 72. Okay, that's going to get me 6.3. That's going to get me 4.3. That's going to get me 0.7. That's going to get me 1.7. That's going to get me 1.7 again. By the way, I'm making all of these positive just right away because I can. Why not? 2.7. And that's going to get me 3.7. So I take all of these distances, right? 6.3, 4.3, 0.7, 1.7, 1.7, 2.7, and 3.7, and I do step 3 and I find the mean of all of that. So step 3 is going to have me add 1, 2, 3, 4, 5, 6, 7 of these guys and divide it by 7. So let's find out what these numbers added up together are, because I have no clue. That becomes 21.1, and 21.1 divided by 7 is going to be 3.014, so we'll do 3.01. Not the prettiest sight, but we did it. State whether it appears to be a positive correlation, negative correlation, or no correlation. Whether this is when there is a correlation, identify the relationship as linear, quadratic, or exponential. These dots, for the most part, appear to be going down and to the right in a straight line fashion, which means I can draw a straight line that best fits the data kind of smack dab in the middle of everything. By doing that, we recognize that that is a negative correlation. And since I can draw a straight line that seems to best fit the data, that is going to be a linear correlation, or a linear relationship, I guess we can say. Pretty strong linear relationship. I mean, it's obvious where these dots are going. So yeah, I would say that that is a strong negative linear relationship. Fun. State whether it appears to be a positive correlation, negative correlation, or no correlation. When there is a correlation, identify the relationship as linear, quadratic, or exponential. Well, I am going to argue that this is a no correlation. If you're like, whoa. Those dots kind of look like they're going up and to the right. They kind of do, but these two dots right here, and yeah, there's two dots, show me that the data is actually going back down. So I'm going to argue that if this information was to keep on going, it would look like this and come back down to earth at some point, which tells me that there is no correlation. It's not positive, it's not negative, no correlation. But since it is going up and coming back down, I would argue that this is a quadratic relationship. Okay? No correlation, quadratic relationship. That's what I'm going to go with. The oyster population of the Chesapeake Bay has been in decline for over 100 years. This is terrible. This can be expressed by the equation y equals 41.6 times 0.969 to the x, where x is the number of years since 1990 and y is the amount of oysters harvested in metric tons. What does the y-intercept of this function represent? Well, it looks to me that my y-intercept is going to be somewhere around like the 40-ish range. So we'll say about 41 or 42. Okay, now the y-intercept happens when the x-axis is at 0. When the x-axis is at 0, that means 0 years since 1990. So we can say 1990, in 1900. So magic happens here at 1900. And according to my y-intercept, which looks like it's a little above 40, all right, that represents 40 metric tons of oysters. So we can say in 1990, or just 1900, in that year, the amount of oysters harvested is a little more than 40 metric tons. So like, 41, 42, something like that. Who knows? Who knows? Who knows? Who knows? But that's what it means. Y-intercept means what happens at the very beginning. And according to this, the very beginning when x is 0 is when it's 1900. And that, ladies and gentlemen, is Algebra 1.